Every day, the world consumes about 100 million barrels of crude oil. It goes into cars, trucks, aircraft, ships, power plants, and factories on every continent. It heats homes, it makes plastics, fertilizers, medicines, and road surfaces. Modern civilization runs on it in a way that has no real parallel with any other single material. But here is something almost nobody knows. Crude oil, exactly as it comes out of the ground, is useless. You cannot put it in a car engine. You cannot burn it in a jet engine. You cannot use it to heat a home. Raw crude oil is a thick, dark, foul-smelling liquid that would destroy any engine it touched. Before it can power anything, it has to be completely transformed, broken apart, separated, reassembled, and chemically altered in one of the most complex industrial processes ever built. That process happens inside an oil refinery, and the engineering behind it is almost nothing like what most people imagine. Crude oil is not a single substance. It is a mixture, sometimes thousands of different hydrocarbon molecules all blended together, ranging from extremely light gases to extremely heavy, nearly solid compounds. What makes crude oil from different parts of the world look and behave differently is simply the proportions of these molecules in the mixture. Light, sweet crude from West Texas is pale and flows easily. Heavy crude from Venezuela is almost as thick as tar. All of it starts with carbon and hydrogen atoms bonded together in chains and rings of varying lengths. Short chains, molecules with just a few carbon atoms, are light, volatile, and easy to ignite. These become things like propane and butane. Medium chains become gasoline and jet fuel. Longer chains become diesel and heating oil. Very long chains become lubricating oils, waxes, and asphalt. The refinery's first job is to separate these molecules by length. The tool it uses to do that is heat. The first major structure a crude oil shipment encounters at a refinery is the atmospheric distillation unit, a steel tower that can stand 60 meters tall, surrounded by pipes, pumps, and heat exchangers that make it look from a distance like something between an industrial cathedral and a piece of abstract sculpture. Inside that tower, the crude oil is heated to around 350 degrees Celsius before being injected into the base as a mixture of liquid and vapor. As it rises through the tower, it encounters a series of horizontal trays, perforated steel platforms spaced at intervals throughout the height of the column. Here is the key principle. Different hydrocarbon molecules condense back into liquid at different temperatures. Light molecules stay as vapor longer and rise higher before condensing. Heavy molecules condense quickly and fall back toward the bottom. The result is separation by weight. At the top of the tower, where temperatures are lowest, you collect the lightest fractions, naphtha, the raw material for gasoline, and gases like propane. In the middle sections, at intermediate temperatures, you collect kerosene and jet fuel. Lower down, diesel and heating oil condense out. At the very bottom, the heaviest material, a thick black residue called atmospheric residue, collects and drains away for further processing. 1 barrel of crude oil enters. 12 or more different product streams exit from different levels of the same tower, simultaneously, continuously, around the clock. The distillation tower never stops. It cannot be switched off without an extended shutdown procedure that takes days and requires the entire unit to be carefully cooled, emptied, purged, and prepared for maintenance. In normal operation, refineries run continuously for 3 to 5 years between scheduled shutdowns, operating 24 hours a day in all weather conditions. But distillation alone does not produce enough gasoline to meet demand. This is a fundamental problem that engineers solved in the 1930s, and the solution is one of the most important chemical engineering breakthroughs of the 20th century. A barrel of crude oil naturally contains only about 20% gasoline range molecules, but demand for gasoline is far higher than demand for heavy fuel oil. If refineries could only distill crude oil, they would constantly be drowning in heavy products they could not sell, while running short of the gasoline the market needed. The solution is cracking. literally breaking the long hydrocarbon chains of heavy oil into shorter chains that fall in the gasoline and diesel range. The primary cracking unit at a modern refinery is called the fluid catalytic cracker, or FCC. Heavy oil from the bottom of the distillation tower is mixed with a fine powder catalyst, a specially engineered material based on zeolite, a mineral with an extraordinarily complex, microscopic structure full of channels and pores that the hydrocarbon molecules enter and interact with. When the heavy oil contacts the hot catalyst at temperatures above 500 degrees Celsius, the long carbon chains break. The molecules crack into shorter fragments. Those fragments are separated and collected, and the majority of them fall directly in the gasoline range. The catalyst itself is consumed in the process. It becomes coated with carbon deposits that reduce its activity. But the FCC unit solves this continuously. The spent catalyst is separated from the cracked vapors and carried by airflow to a regenerator vessel, where the carbon deposits are burned off at high temperature. The regenerated catalyst flows back into the cracker. The whole cycle runs continuously, with catalyst circulating between the reactor and the regenerator in a continuous loop, processing thousands of barrels of heavy oil every hour. The FCC unit is, in a real sense, what makes modern gasoline supply possible. Without it, a barrel of crude oil would yield a fraction of the gasoline a modern refinery produces. With it, refiners can push yields far beyond what distillation alone would allow. Even after distillation and cracking, the products are not finished. Most of the streams leaving these units contain sulfur compounds, nitrogen compounds, and other impurities that would cause engine damage, produce harmful emissions, or fail quality standards. The treatment process that removes these impurities is called hydrotreating. The product stream is mixed with hydrogen gas at high temperature and pressure in the presence of a catalyst. The sulfur and nitrogen atoms react with the hydrogen and are removed as hydrogen sulfide and ammonia, gases that are captured and processed rather than released. The hydrogen used in this process is enormous in quantity. Large refineries consume more hydrogen than almost any other industrial facility. Much of it is produced on site from natural gas through a process called steam methane reforming, which is itself a significant industrial operation running continuously within the refinery complex. Modern fuel sulfur standards are measured in parts per million. The gasoline in your fuel tank contains perhaps 10 parts per million of sulfur. The crude oil it came from may have contained tens of thousands. That reduction, by a factor of thousands, happens in the hydrotreater, quietly, continuously, as part of the standard refinery process. There is a detail about refinery operation that most people find genuinely surprising. A large modern refinery does not simply process crude oil into fuel. It is, in a meaningful sense, a chemical factory that happens to produce fuel as its primary product. The same processes that produce gasoline and diesel also produce feedstocks for plastics manufacturing, raw materials for fertilizer production, base oils for lubricants, sulfur for agricultural chemicals, and bitumen for road surfaces. The plastic in a water bottle, the fertilizer that grew the wheat in a loaf of bread, the asphalt on every road surface, all of it originates in the same crude oil barrel that also produced the gasoline in a car tank. Refineries optimize continuously for the most valuable product mix given the crude oil available and the current market prices for each output. When gasoline prices are high, refiners push cracking capacity harder to maximize gasoline yield. When diesel commands a premium, they adjust the distillation cut points to favor middle distillates. This optimization happens in real time, managed by control systems that monitor thousands of process variables simultaneously and make adjustments to maintain product quality and maximize value. The scale of a major refinery is difficult to convey in abstract numbers. The largest refineries in the world, facilities in India, Saudi Arabia, South Korea, and the United States, process over 600,000 barrels of crude oil every single day. That is roughly 95 million liters per day. The pipe networks within a large refinery can stretch hundreds of kilometers in total length. The heat exchangers, devices that recover waste heat from one process stream to preheat another and dramatically improve overall energy efficiency, number in the thousands. The pumps, compressors, valves, and instruments are counted in the tens of thousands, and all of it operates continuously in all weather for years between shutdowns. The engineers and operators managing a refinery are not running a process that starts and stops. They are managing a continuous flow system where the consequences of a mistake can propagate through multiple interconnected units simultaneously. The most catastrophic refinery incidents in history have involved the same basic mechanism: a loss of containment, a pipe failure, a valve malfunction, a pressure excursion that releases flammable or toxic material into an environment where it finds an ignition source. The systems designed to prevent this, pressure relief valves, emergency shutdown systems, flare stacks that burn off excess hydrocarbons safely, are as engineered and as critical as the process units themselves. The crude oil that comes out of the ground is the beginning of a process, not a product. Before it can move a vehicle or heat a home or become the plastic case on an electronic device, it passes through a series of units: distillation, cracking, treating, blending, each one designed around a specific chemical principle, each one operating continuously for years. The refinery that does this work is not a simple processing facility. It is one of the most complex continuous operation engineering systems ever built. The chemistry is sophisticated, the scale is almost incomprehensible, and the margin for error, given the temperatures, pressures, and flammable materials involved, is essentially zero. Next time you fill a fuel tank or open a plastic bottle, the crude oil that became those products went through all of this first. Hundreds of kilometers of pipe, thousands of instruments, temperatures above 500 degrees, hydrogen under high pressure, a catalyst circulating between a reactor and a regenerator in a continuous loop, all of it running without stopping, around the clock, on every continent on Earth.